Hello, AP Statistics. This is Chapter 11, Lesson 11.1, the chi-square test in the Practice of Statistics book that is with the flamingos on the front. Okay, day 1. So this is following pages 680 to 687. All of the variables in this chapter are categorical because we're studying chi-square. So we're wondering about the distribution of the proportion of M&Ms that are each color in the bag. Or we're wondering about the distribution of people with opinions from very strong to very much don't care, not influenced. Okay, so a chi-square test, and that's written like this little fancy x squared, test for goodness of fit. That's the first test that we're going to study, and the only test for section 11.1 is it compares an observed difference of observed data to the hypothesized distribution. So what that means is that we're comparing if we opened up a mega bag of M&Ms, or maybe many mega bags of M&Ms, and then counted all the M&Ms and sorted them all by color, and we counted how many M&Ms are each color, and then we called that our observed data, but then we looked up the distribution of color online on Mars website and found the true stated distribution of M&M colors, and then we went to compare our observed distribution to the stated distribution. Then we would be looking at a chi-square kind of statistic here, where we would be wondering what the probability is of getting a distribution like ours, given that the stated distribution is true. Okay, how will the data look? How will I identify if I need to do a chi-square goodness of fit test? The data should be in a one-way table. So I just have brown, blue, not black, brown, blue, yellow, orange, I'm forgetting other colors of the M&Ms, green, red, okay. And then the counts of those M&Ms, and that's it. Okay, it doesn't have two data variables on left side and the top side of a table, and then have data inside there, just one categorical variable. Okay, the data may be shown in a one-way table, and the data displays the distribution of one categorical variable in one sample. What are the null and alternative hypotheses for a chi-square goodness of fit test? The null is that the stated or the hypothesized distribution of the categorical variable is correct. So we're saying that of the two ideas here, hypothesized distribution and the observed distribution, that the hypothesized one is correct. Okay, that means that essentially the observed data is equal to the hypothesized data to a certain degree that we can't discern the difference, and that we don't feel that that the hypothesized distribution is lying. Okay. The other HA is that the stated hypothesized distribution is not correct. Okay. Not correct, or is different from the data that we got, is the idea of a not equal to sign in an alternative hypothesis, and that's two-sided therefore, and it's always going to be two-sided. Okay. So we will never have like less than or greater than in an alternative hypothesis for a chi-square. We'll just have that it's not correct. Okay, always in terms of the population, remember. Therefore, there's no p-hat notation in these hypotheses. Always use p's and always refer to it as the true distribution. Okay. Okay. How do you calculate the expected counts for a chi-square goodness of fit test? Should you round these to the nearest integer? The expected counts are the sample size times each of the proportions that we expected in that category. So the sample size times the category population proportion. Okay, populations here because we're referring to the expected counts, we're referring to the hypothesized distribution, okay, and proportion because we're going to times each sample size times the proportion of the total sample or the total population we should have expected in our sample. And this is a lot like finding the expected count back in a random variable chapter. Don't round the expected counts to whole values. If you remember that from the random variables chapter 2, we said that expected counts can go ahead and be decimal values, and we said that we realized that that's not naturally occurring with random variables most of the time, especially discrete random variables, but that we're okay with that, and we realize that this is kind of a long run kind of idea. So however, in chapter 10, realize that when we did this large counts condition, that when we found our successes and failures, that we did round to whole values. So just make sure that you're keeping track, running total of all the chapters that we've covered, that you know when to round and when not to round. Okay. Also, these represent the average value expected in repeated samples. So if we were to sample over and over and over again, then these are kind of theoretical expected values and hence the decimal values. Okay, what is a chi-square test statistic? It is chi-square equals the summation of observed minus expected squared over expected. Now, when we take observed minus expected, we could get positive or negative numbers depending on if observed or expected is larger, but when we square it, all these values become positive. So when we take a summation of a bunch of positive values, chi-square is going to be all positive. Use counts, not proportions, when you take observed minus expected. When you revisit this chapter after a couple weeks, you'll be like, oh, what are we doing again? Okay, yeah, use counts, not proportions. All right, is the formula in the formula sheet? Yes. What does chi-square measure? Chi-square measures how much different the observed distribution is from the stated or the hypothesized distribution. Very, very large values of chi-square indicate that the hypothesized distribution and the observed distribution are quite different. But smaller values of chi-square are not evidence of a statistical significantly different distribution in your observed distribution of your categorical variable. In a goodness of fit test, when does the chi-square test statistic follow a chi-square distribution? When all expected counts are greater than 5. That's kind of your new large counts condition. How do you calculate the degree of freedom for a chi-square goodness of fit test? The degree of freedom is the number of categories minus 1. Okay, so if you had your M&M distribution and it was like blue, brown, red, orange, yellow. Okay, let's say we have those 5 colors, then we would take 1 away and we'd say our degree of freedom is 4. Okay. Realize that doesn't have anything to do with sample size then, so it's quite different from your previous 2 chapters. Okay, describe the shape, center, and spread of the chi-square distributions. How are these based on degrees of freedom? The shape, chi-square is only non-negative, meaning it's only positive. Here's kind of a little sketch of an idea of a chi-square distribution. If chi-square equals 0, then there's no difference between the hypothesized distribution and the observed distribution. Now what that means is that back here, we had this formula, and so if our expected counts were equal to our observed counts, then we'd have 2 values that are equal. And when we subtract them, we'd have 0. 0 squared is 0. 0 divided by anything is 0. When we sum up a bunch of zeros, we get 0. So chi-square would be 0 if our observed counts and our expected counts are all exactly the same. If chi-square is really large, then it is statistically significant and you are not likely to observe a distribution like the one you did by chance alone. Therefore, the distribution is skewed right, okay, because of these 2 things. It's only non-negative, so it's positive. And if chi-square is 0, that means that there's no difference between the hypothesized distribution, but very large values are very unlikely to have occurred by chance alone, so there's very little chance of very high values of chi-square. Okay. And then here's just some like side information about chi-square because so much is known about chi-square because it occurs across so many disciplines. So the mean is equal to the degree of freedom. Its peak is at degree of freedom minus 2. And the standard deviation is 2 times degree of freedom square rooted. How do you calculate p-values using a chi-square distribution? Table C or second distribution option 8 chi-square CDF, lower upper degree of freedom. Realize it's already when you have a chi-square value, so that's just the quick route to getting your p-value. Okay, an alternate example, a fair die. Jenny makes a 6-sided die in her ceramics class and rolled it 60 times to test to see if each side was equally likely to show on top. State the hypotheses Jenny's interested in testing. Her null hypothesis is generally that each side is equally balanced, kind of like her no change hypothesis. The stated distribution of the categorical variable is correct. That would just mean that in this context that her die is equally balanced. So each side of the 6-sided die is equally likely to land face up. Or you can say that the proportion of 1s and the proportion of 2s is equal to the proportion of 3s and 4s and 5s and 6s, which is equal to 1/6, which is equal to the decimal point 167. But if you go this route and you put this out in symbol form, you can't just leave your HO and move on to your HA, because what did you do? You introduced a variable. If you start talking about proportions of each of these things, 1s, 2s, 3s, 4s, 5s, 6s, you must define what P1 to P6 means. So if you want to write that out, you still have to follow it up with a detailed sentence saying where P1 through P6 stands for the probability of getting a 1 through the probability of getting a 6. That's a lot of words. That's about as equal to this many words. So I would just say go this route to begin with and just put it in sentence form instead of in equation form, but it's all your own style, and you can see which way the back of the book decides to do it. You can compare with the way I did it, and you can decide which you like more. All right, so each side of a six-sided die is equally likely to land face up. Or the alternative, each outcome of the six-sided die is not equally likely to occur. Now, realize that maybe like 1s, 2s, 4s, and 5s are all equally likely to occur, and they all occur at a 1 to 6 ratio. With a 1 in 6, 1/6 of the time. But then maybe let's say that the 3 and the 6 does not occur 1/6 of the time. The 3 occurs more often and the 6 occurs less often than it should. Then we don't have a balanced die. So all that it takes is 2 of those proportions to not equal 1/6 to also mean that you have evidence of the alternative hypothesis being true, where not every outcome of the six-sided die is equally likely to occur, okay? Or this alternative wording. So, assuming that her die is fair, calculate the expected counts for each possible outcome. So the expected counts are hedging the bets that she has a balanced die. So for a fair die, 1 of 6 outcomes has probability 1/6. The expected count is n times each of the proportion. Well, each proportion is all 1/6. But so we do 60 times 1/6 to get 10. And we just repeat the same math over and over and get all 10s. So for all 60 rolls, we would expect 10 1s, 10 2s, 10 3s, 4s, 5s, and 6s. The table shows the results of Jenny's ceramic die rolls. What is the evidence for the alternative hypothesis? The evidence for the alternative is that the die is not equally balanced, and the evidence is that 3s occurred a little bit less than they should have, and that 1s occurred a little bit more, and then, a little off on all the other ones except for 5s. So the observed counts are not all equal to the expected counts. Calculate the chi-square test statistic. Chi-square is equal to each of these observed minus the expected squared over the expected. So we have 13 minus 10 squared over 10, 11 minus 10 squared over 10, 6 minus 10 squared over 10, and so on for each of the components, 12, 10, and 8. Okay, then what I did is I worked downward and I showed each of those components so that I can look at them and do a little analysis afterwards. Chi-square, though, is equal to the sum of all 6 of those components, and it's 3.4. Note for later, this was the largest contributing component to our chi-square, the largest of all 6 components. This is important because very large values of chi-square tend to cause us to reject the null hypothesis and conclude the alternative. And if we're going to conclude that she did not make a balanced die, we're going to hurt her feelings. We might as well be really sure about that, and we might as well have a little bit of information to back that up. And it'd basically be the largest components that jack up this number really high, that are causing this number to be large, that are causing us to reject the null. So therefore, it'd be this value here. She had too few 3s. Okay? Anyway, let's just take a look at this before we get ahead of ourselves. Find your degree of freedom first, then you can find your p-value once you've defined the this particular chi-square distribution. Degree of freedom is 6 because we have 6 categories, minus 1, which is 5. In the table, we can use degree of freedom 5. Look for 3.4, we don't see it, but we see 6.63, which is the closest to it, and it gives us a p-value of greater than 0.25. That's pretty far from rejecting. Using technology, we go chi-square CDF. 3.4 is the lower bound, 10,000 is the upper bound, because you know that chi-square, we're always going to find a right-sided chi-square area, because we're going to find the probability of getting some distribution as extreme or more extremely different from the expected counts in this and right here, and since chi-squared is skewed right, we would find a right tail area at all times Okay. Anyway, so we get lower upper degree of freedom. We get a p-value of 0.639. Very large p-value. Because the p-value of 0.64 essentially is greater than alpha equals 0.05, we fail to reject HO. There is not convincing evidence of the die being unfair. Remember, don't write language like you sound like you're accepting HO. We are not saying that it is a fair die. We're just saying that there's not evidence of it being an unfair die. If the conclusion in part F is an error, which error did we commit? Explain. Now, we could have committed a type 2 error where we failed to reject HO when HA is true. We didn't find convincing evidence of an unbalanced die when really it could have been unbalanced. Okay, so even though we didn't find evidence of an unbalanced die, which you might be suspecting it is unbalanced, because who's Jenny? Is she really a die maker? Who can honestly pack a little die in clay just perfectly? Okay, pretty hard to do probably. So we might want more data, okay, to finally really feel like we rejected correctly. But anyway, this is all one-shot deal right here. So there you have it. There's kind of a first run through chi-square. Good luck.